Welcome! At the Gate4SPICE gathering in May, we looked at several aspects of machine learning and which aspects are covered by the current version of the Automotive SPICE and which aspects are not covered. After initial discussions, we conducted a workshop to solicit the collective intelligence of the group gathered. And so, without further ado, let's listen into the initial discussions, starting with an overview of ASPICE and following with an overview of machine learning. Please note that the workshop is not covered in this recording.
Automotive SPICE. As one of us explained, that it came out of the automotive OEMs that said, we are having problem with quality of the product that comes out of our suppliers, so we got to get something that a mechanism to identify how good they're gonna be before the product shows up at our door. And so Automotive SPICE is the assess model. In the aspects, it has like two-dimensional. There is processes, and you see that in the horizontal column, and then you were gonna see the level of capability achieved per process. We're going to see more specifics on that. This picture, maybe most of you guys seen here, what it represents, all the processes make up the Automotive SPICE, and the dark pink ones are the ones what we call VDA scope, where they say, this is the basic scope we usually assess our projects, their suppliers' projects, when usually the OEMs are asking for it. What you see here is ultimately best practices. The OEMs decided, here are the best practices should be done. For example, you see in the middle, the V cycle, all the way from system requirements, analysis, architecture, and then down to the software, all the requirements, architecture, detailed design definition, and then back up on the right-hand side now, all these good things we defined, and even we created the software for it. Now we want to see, did we meet what we said we were gonna be as our requirements, architecture, design on the left-hand side. So on the right-hand side, we test each of them and goes all the way up. And in addition, there is the supporting processes. We want to talk about performing quality assurance of our work products and processes. We want to make sure all the work products we produce are managed well via the configuration management. Problems, changes are managed. And also, of course, project management that you see on the right top is one of the key process areas, because all these activities has to be planned. You got to have people to do it, track all that work. So also the supplier monitoring is one of the VDA scope processes. So you each have one of these handbooks or pocket guides. It contains these processes, and we will actually use them in the work later on. And what is in the Automotive SPICE per process? In there, this is an example for the software unit verification. It has the process name, ID, and then purpose. Purpose is something that I really like, where it's not just about do this, do that, but here's our purpose. Also, it has process outcomes. That's part of the what we check at achievement of capability level 1. We look to see if we achieve the outcomes for each of the processes. In addition, for how you achieve these outcomes, there are base practices. And each of these you will also see in your pocket guide. you can think of them as the activities you're performing so that you can achieve those outcomes. And you will see that for each of these base practices, there's a tag. It says, for example, outcome 1, and this one helps you achieve the outcome 1. And then there's also notes. Notes are useful to give a bit more clarity. What do you help with the interpretation or give some examples of it. There is also the output work products defined as part of the Automotive SPICE. Those are, you don't have to have exactly those. They're examples. You can clearly, just more important, you have the information in some work products. They are not, let's say, explicit that you have to have these work products. So in an assessment, we will be evaluating for, let's say, capability level 1, if the outcomes are achieved by looking at the base practices. Automotive SPICE has various capability levels. In today's event, when we do the workshop, we're going to be focused on capability level 1, which is actually the hardest step in my mind. When you go from, let's say, here's a concept, here's a prototype, how do we make this go into 1 million cars? It's the hardest step to achieve because it's very comprehensive. After every capability level, after that, it's trying to make it that it's actually, you didn't achieve the outcomes just by chance, but you actually managed it, so obviously capability level 0 is the outcomes are not achieved. That's clear. Capability level 1 looks to see, did we achieve the outcomes? In capability level 2, you have 2 aspects. Did we manage the performance of the way we're working, our processes, and also are the work products managed effectively for quality of the work products and configuration management of the work products? Now that we have all work products and the way we're working are managed, we are now looking, the next capability level is capability level 3, which maybe is now, hey, we got in this one project, we have some cool way to do this. We can achieve capability level 2 in the way we're working. Why not take this and share it as a standard in our organization? Say, oh, okay, here is the way we can work. Define our standard processes, and now as part of this, we can then deploy them to future projects. And they can then benefit from all the learnings and best practices done in the multiple projects. It also enables you that you can share once it's deployed to multiple projects, learnings from multiple projects are coming in, you can improve the standard process too. So usually in our assessments, we will be doing, up to capability 3. We have not done any capability level 4 or 5 assessments. Have we, Boniface? We have?
We did, but very rarely.
Very rarely, right? I myself haven't. And to get to the capability level 2, level 4, now we are doing analysis in terms of we have data in how well we are performing and make it predictable in the sense, and we're able to manage that standard process with qualitative and quantitative analysis and control it. And capability level 5 is going to enable us now that we know we have all these improvements that can be done based on concrete data, we can then now innovate and come up with different ways of performing our work so that it can be more efficient, it can be better quality. So that's general what I wanted to regarding Automotive SPICE. Do you have any questions regarding Automotive SPICE at this level? Something you would like to?
This applies for autonomous cars category as well, or?
Yeah, it will be any kind of a product. And now, of course, when you come to the autonomous, you're going to talk more about machine learning aspects as well. And in this Gate4SPICE, we're going to check to see current version is 3.1 of the Automotive SPICE. How well is it addressing the way we work on the machine learning so that evaluation of project using machine learning development then is effective. There is potentially, we're going to identify things that is done in machine learning not necessarily covered in the current processes in the standard. And so we are, Boniface also mentioned the new version coming up, 4.0 of Automotive SPICE, maybe next year, hopefully. These things are challenging the exact timing. Multiple organizations, companies are involved in these discussions. And so but machine learning is targeted to be addressed more specifically as part of the 4.0 as well. So this is our good opportunity to be able to give feedback to that, to say, this is what we see, what we think from our Gate4SPICE event here. And some specific aspects most likely not covered in the current standard.
I have a question as well. With more driver assistance features coming into cars, this software is going to take control of the car, like for automatic emergency braking and automated driving and those concepts. So, Mr. Mark, you said OEMs were interested in the software quality of suppliers. So now my question is, are governments and regulatory bodies also thinking of constructs like ASPICE and, to see if there's any value in ASPICE and start mandating down across the industry? Is there any talk around those fronts?
Yes and no. When we talk about Automotive SPICE, regulators don't focus on that right now.
Okay.
But they focus on other areas. And one of them that is really critical for OEMs because it's homologation relevant. So you can't put cars on the road if you don't can demonstrate compliance with certain standards is in the field of cybersecurity.
Okay.
That is definitely one they shoot for. The standard is ISO 21434 and the so-called UNICE regulation.
25100.
And the other one is a bit more indirect, also not explicit, with the focus on homologation, but more from a product, let's say, liability perspective, which is functional safety.
Okay.
And there we also have a touch point to automatic drive and machine learning. So obviously the system will be safe as well.
Right.
So there's an indirect correlation, indirect, let's say, way how they assess it, but not a specific.
Yeah. Not through ASPICE. There is different approaches. They're trying to manage the expectations, but not exactly from ASPICE.
So I have a question.
Please, Alex.
So what we are seeing is ASPICE 3. Like level 3 is typically what OEMs task us to do. What are the examples of like level 4?
What are the examples of a level 4?
Yeah, level 4.
How will it look like?
No, but like what is the specific project that would require like this level?
Oh, why OEMs are not asking for level 4 or 5? You're trying to say? Why are they?
It seems like rarely they do. So I'm curious, just like what kind of projects would be like to ask for like high level ASPICE?
Well, do you remember what was the project? Why they were going for level 4 or 5?
Well, I just looked up in our database, and there are many assessments in there. So I did some quick math, and we talk about 0.4% of organizations level 4 and level 5. And one of these organizations, I remember both of these assessments. It was never about the request of the OEM. It was always about the internal motivation of the organization to get a bit better. And when we talk about level 4, we talk about statistical process control. And to go for statistical process control, you need to have a very homogeneous set of projects that are continuously done the same way. And to have that kind of stability in an organization, especially these days, is rare. So for most organizations right now, the reason why they don't go for level 4 and 5 is they don't have the databases to really justify something like that. Back in the old days of CMMI, it's still around, but not for automotive. The motivation was more like I get data that help me to do my improvements in my process more, let's say, focus with the support of statistical process control. So again, more efficiency can drive my test efforts in a better direction. It's more like efficiency gains, and the OEMs are not really interested in that at all. They say we want to have good quality. How you achieve it, if you're efficient or not, is your problem.
Right.
We focus on the output of science.
I worked in defense late 90s. It was mandatory that you do CMM level 5 and CMMI level 5. And you had to achieve that in order to put your software to military ground vehicles. Even in aviation aerospace, you had to have higher standards for paying to fall for your own vehicle to shoot on its own. So there's more strict standards that were forced by them.
Right.
And it's expensive. Sure.
Right. I mean, efficiency is a business goal for the company, right? And in a way, I see the producing good quality product is a great way to becoming efficient, because now you do not have to deal with the rework, or it's minimize your rework effort. How you could still produce a good quality product, but in a more efficient way, you can still work on that, right? That's kind of we are coming to when you move up to capability levels. And I guess in the end, Automotive SPICE needs to be a business decision by the organization, right? To say, here is the business value of improving the way I work, our processes. And based on this, if you can justify that, hey, it's worth, why not keep going? And ultimately, we have to keep improving, and potentially it may even be reaching up to capability level 4 or 5 in some areas. Maybe you don't hit every process because each process is assessed separately. But in some processes, maybe it's really critical to the way you're working in terms of efficiency. Then why not? It's a business decision in the end. Do you know of any other alternatives covering software similar to Automotive SPICE? We have CMMI, but is there anything else? I can't.
Well, yes, there are many standards like that, but they are always industry specific. So there's a SPICE, for instance, for medical.
Medical, right, industry. You were asking for automotive industry. Yeah. Automotive industry, we have the two, the basic Automotive SPICE, right?
Well, you can say automotive is really ASPICE.
ASPICE, right.
Even the last companies that did go CMMI in the very beginning, BMW was strong.
There are some.
CMMI, Bosch was strong in CMMI.
Right.
But all of them changed.
They are changing now all to Automotive SPICE, right? Automotive SPICE is the automotive industry standard for development. And what we didn't discuss, that it's also not just software. In the processes we saw, it was covering software. It also now has electrical and mechanical, kind of take the bottom of the V out and you can plug in the mechanical parts. It's corresponding mechanical processes or electrical processes as well. So you can look at those as well now. So yeah, Automotive SPICE is the standard, is our known best practices of developing automotive products. Now,
we have exposure to those like vertically integrated for service providers. Let's call them this way. So like Cruise of the world, Waymo of the world. Like what is their process? Like it seems like they're coming up with like their own framework. What is safe? What is not safe?
oh, you're talking specific from the safety perspective, or?
Yeah, the safety is the most critical, part of the story, right? So it doesn't look like they're like at least like solely relying, on ASPICE, right?
Yeah, Automotive SPICE provides a good foundation in terms of being able to produce safe products, but not sufficient. So you will perform, compliant, you develop your products compliant Automotive SPICE, plus in terms of automotive safety, you will need to be compliant with ISO 26262. That is the accepted best practices that we check to see, okay, is the product safe? That's our industry best practices. So you asked about Waymo?
Yeah, there are a bunch of companies. So like every day they coming up with like a new framework how they do safety.
Yeah, I'm not familiar with Waymo, or do you know both of us?
Yeah, I know a bit about these companies, and all of them follow different strategies. When we talk about safety, it's really about liability at the end of the day. So if a company is willing to accept that they pay $1 billion for whatever, or a couple of billions, then they don't need to follow the standard. And some companies gamble a bit more than others in that regard. I have to admit, quite frankly, that's my personal opinion, I don't like gambling with life. So therefore, I would expect every company to really follow the standards, but unfortunately not all do. I'm definitely not talking about Waymo right now, so it's more general thing, so don't get me wrong. Nevertheless, there's one thing, if you really want to go for production, the cybersecurity thing is the most important and strict one for OEMs. First of all, there is no safety without security.
Right.
That's a general rule. And that's meanwhile also in the 2026-262 standard. So therefore, companies must follow, and they want to go for production, for homologation, at least in the majority of the markets on the planet. We talk about China, we talk about all over Europe, we talk about Korea, we talk about Japan. US is a bit different, but when you want to sell cars in these markets, then you have to be compliant with cybersecurity, and most companies then also follow.
Yeah. So hopefully, as the companies realize, where did it come from is these major recalls, where resulted in people getting hurt and died, and eventually the cost of this to the OEMs or the suppliers, they just disappears. For example, Takata.
May I add one thing?
Please.
Safety, I think there's one important statement in the scope of the standard 26.26.2 and also for cybersecurity. They always talk about production vehicle.
Yeah.
So everything that is considered not production vehicles, so test vehicles, etc., they are exempted from following standards. If you look at what Waymo does and a couple of other companies, they are right now, let's say, in a
prototype.
Prototype. It's not considered production.
I think they're starting to charge money for it. So essentially it's production.
Then probably they start to go in that production space, which is then maybe kind of a gray zone. But the standard explicitly asks for production.
But the dynamic is kind of interesting, right? So you would imagine they would try to calculate and there's some sort of industry standard, but this is not what they do right now. Each company does something different.
Yeah.
In the long run, there will be some kind of industry standard because not following a standard drives, let's say, organizations crazy. because there are always tier ones involved, and they say, oh, we should go left with these guys and we should go right with that guys. It stopped the effort, it just increases the price. And automotive is super competitive also on the price side. So efficiency is an important aspect there.
Right.
Standards help to be more efficient.
For sure.
So if all do it left, then it's good for everybody as long as it is not really relevant for competition. And 99% of the software, it's maybe a bit exaggerated, but let's say 90% of the software that gets developed for automotive is not relevant for competition.
Yeah. If you could have a product that you producing good quality, safe product, delivering it when you said you will deliver, then you will be maybe especially efficient because of you don't have as much rework. Now your customer is now knowing that, okay, when they get the product from you, it's going to work as intended, and you're going to deliver it on time. You can charge more, in my mind, and the efficiency you gain from not dealing with all that rework, it's more profit for you, right? It's in the end, companies are here for business, right? So if they make that connection, then I think you'll be more interested. Everyone in the companies, everyone in the organization, not just this one quality guy talking about, hey, let's figure out some compliance. Everyone will be more caring and be more conscious about how they do the work. Is the product really producing good quality efficiently, effectively? So it impacts the bottom line. So when they come to that realization, hopefully, it will then, many organizations then start trying to care. And of course, like Boniface said, the life, we're all driving these cars. Our kids, some of you guys, your kids are not, but some of you guys' kids are driving, and we don't want anybody to get hurt. And so hopefully we'll all come to that conclusion. All right, machine learning, and some overview from what I understand, and I'm really happy that we have our machine learning experts here and that they can then help make it more real. So counting on you guys. Thank you for being here on that. And so maybe my thought was that, just go around a little bit, and if you can just tell me what you understand, what is this machine learning is, and maybe we just start with Josh.
The rest of us want.
Oh, well, you all have ideas too, I'm sure. Yeah. What is it, Josh? It's many things. Okay.
People like to break kind of AI and ML.
Well, it's more rational, obviously,
What we talk about mostly in production is like supervised learning.
Yeah.
Or algorithms that we teach based on a data set that we know something about. Just to say that, like, we have some example files and we want to learn, and we know what we want the machine to say about it. So then we kind of train models via that, right? So there's basically like a passing through the model, iteratively updating it, and kind of telling the model how far off it was from what you want, right?
Right.
Hundreds, to thousands, and millions of times, eventually that's pretty good doing the thing that you've asked it to do. It's kind of a correlation machine, though. It's very committed to whatever distribution you want to show it. And so I like to kind of tell people they don't really understand things. They're just like really good at recognizing patterns.
Yeah.
And so a lot of it's in pattern recognition.
Pattern recognition. Okay.
There are other kinds of machine learning too, like clustering and stuff.
That's that unsupervised thing that you just look at it and like, I see something interesting here, kind of thing. Yeah. That seems to fit together.
Exactly.
Okay.
So, and that tends to be clustering and draw like lines around your data and trying to patterns and things about it.
Okay. Okay. Thank you. So that, Alex, would you like to say what is machine learning for you?
Yes, so I'm not a scientist, right? So I'm trying to usually like simplify for myself, like what other folks are doing.
Yeah, good idea.
Just not to go crazy. So like roughly, I'm thinking about it. It's like traditional software. You need like to code like with your own hands, like the behaviors, right? The expected behaviors that you want. So this is kind of like traditional approach.
Yeah.
Machine learning approach is so those behaviors are learned kind of implicitly, right? Just like from data. So you're not coding those behaviors. The algorithm learns from data.
Data.
So it can be both like supervised, unsupervised. So yeah, so and difference between supervised and unsupervised. Supervised essentially requires like data labels, right? That are created by humans. Right, the human will say this is like good, this is bad.
Right.
Unsupervised means algorithm can pick up by itself, like recognize patterns without you even like telling it explicitly what it is. And there is like a huge, of course, like difference between those two approaches. And unsupervised has like lots of benefits, right?
Also?
It has lots of benefits.
Benefits. Well, yeah, it's less work, right? For us.
Exactly.
Much cheaper. Trying to label thousands of data. Yeah, this is that one. It's that one. And like, wow. It's
yeah, so the difference is like huge. It's like 10,000 times, maybe 100,000 times cheaper.
Yeah, it's cheaper.
Jan LeCun, so he's like one of the OGs, the original, neural network guys.
Yeah.
So he always said that unsupervised learning is the cherry on.
Yeah, if you can get that. Yeah. Thank you. So, Erwin, you guys did machine learning back in the defense industry.
Also at MIT.
Yeah, you gotta send that to us. Did you even find it?
No, so I rewrote it for when I was at FCA.
Okay.
But I'm trying to get the original.
So what is machine learning to you?
These two summed it up pretty well.
Okay.
It's basically data collection, how you use it, algorithms for specialized activities that you wanted to do, and your ultimate goal is to be autonomous.
Right.
And unsupervised is the.
As
I like the
unsupervised.
term unsupervised. I'm going to use that.
Okay.
Use of this data.
Got it.
To me, it's the algorithms that are doing the learning and then executing. So,
okay. For you,
a tangible example, like real life example in our daily lives, is we just think or we just search about anything that we want to buy, right? And then we see thousands of options. Ads on here. Even if you go to any social media platform, it's right here.
It's everywhere. Machine learning is everywhere.
I always describe it when people don't know as Spotify.
Machine learning
right,
is
that's machine learning, right? You got your own song list, and they know what kind of things you like, and they're constantly suggesting things. And as you choose things, they'll remember.
Then it's learning, right?
Exactly.
Making the whole playlist for you.
Yes. Yeah.
Right. I made this for you.
And in some ways, when we talk about ASPICE level 4s and 5s, that's what it is, right? It's
learning.
It's learning, gathering some data set, right, about the way you execute your processes, and having and applying that data to say, okay, these are the ways you would improve your processes, right? It's all data driven, right?
Now what we need is the algorithm and train the algorithm on the data we collected on the processes, and it will give us
Better processes, right?
improvements. Wow,
So
we
it's-
don't
so, you
know
know,
what
you-
to do. Thank you
could
so
make
much.
a sort of a hybrid machine
4,
learning, right? To
guaranteed.
sort of get your company toward level 4s and 5s, right? Because
That's
that's what
right.
we're doing, right?
We're gonna, yeah, this
That's
is
what we're
it.
talking about.
That's what we're talking about. We
Yeah.
could then come up
Yeah.
with the trained algorithm.
Sure.
That's our new product.
Tell Peter.
We're, I think,
Put
yeah.
Peter on it, you know.
Yeah, we'll put Peter on this. He'll teach.
Gathering the data, he's good at
Yeah,
that.
that big movement back in the 2000s,
Sure.
it was data mining.
Data mining.
Yeah, and you'd have these computer science wizards algorithms based on what type of data you want to mine. And that's the difficult part. What do you want?
What do you want to? Right,
Yeah,
that's
like
a
big
tough
time.
one.
Maybe Netflix.
That's right. Anybody else wants to add some definition of what, something different or idea of what machine learning is from your understanding?
The one thing I'll add is like we're talking about a very specific part of machine learning. There's a lot of like active learning, online learning, reinforcement.
Yes, we're talking about automotive embedded products.
Yeah.
Okay, right, for sure.
All that stuff's gonna be our headaches 5 to 10 years from now.
Yeah. So I've been looking into this, and idea is that, okay, it is a practice. Machine learning is our practice to use this algorithm, just as you guys said, and then learn from the data and then make predictions about some new data, I guess. That's what I understand. Now, then the question was, okay, if I were to look at the CPU instruction level at the end, this model is produced and it's now able to predicting, maybe it's looking like the code that came out of, it's similar, it still has logic and calculation and things at the CPU level instruction, right? It's running on our processor. So it's producing software, like I think one of you guys said it's produced, I think maybe it was Alex, you're saying producing the software instead of writing in hand, it's producing it through data learning. And does this mean that all right, well, this is a cool new way of creating software? It turns out, in my understanding, is the machine learning is targeted to solve maybe excels at certain areas. Traditional software is going to be there to deal with more human level complexity, but more broad problems. Machine learning is a bit more narrow problems. Says, okay, detect these traffic lights. Maybe it's really specific, or this more, and at least my understanding is it's more on the level of complexity and the how narrow the topic is makes a difference. So some of you guys mentioned that the different usages of the machine learning. And so the kinds of problems it solves is like, then there is complex, because there's so many possibilities. So as human, we can't simply kind of come up with the logic to write the code directly from it. And there is data available on this, but it's so you could simply have something that detects kinds of the animals. We have the examples. I think, Robert, you mentioned about the driver monitoring. To do the automated driving, we have to detect all these traffic signs. There is predictions regarding maintenance, wear and tear of in automotive. So there is machine learning is used, and also the obviously the detecting cars, vehicles, all the things surrounding the car, lanes. All these are the kinds of problems machine learning is used for. And so it has repeated decisions, and it's difficult to come up with what is the criteria should be. It's approximating. It's coming to a certain prediction accuracy, saying, okay, most likely with that prediction level, it's this. You know, it's a husky or it's a wolf, but it's not as deterministic as like the simple logic in our regular software. And we got to have data on the representing what the problem is. There is lots of terms. Some definitions that I gathered here is I mentioned about it approximates the behaviors, what's the machine learning is. It learns from these data examples, it approximates it. And all these terms are making up the language we use when we talk about machine learning. So some interesting ones is the neural networks, of course, is one of the ones kind of like in our brain. When we learn, these neural network nodes, they fire and then makes another connection, and those connections get maybe stronger. Then we now follow that path more often than some other path as we come to the same kind of similar scenarios. It's similar as that. And there is this deep learning thing. How deep is it? It's like, okay, now it has multiple layers of how deep is the network? And it seems that you could technically have each of these layers to focus on certain aspect of it. And this thing does the color and the next thing does the shape or whatever. You could organize it as such to finally say, this is a stop sign or whatever it might be. Of course, we got data. The algorithm is it's the core code, right? This is usually some kind of a mathematical formula. And then maybe in each of these nodes, you have some weights or you apply some function into the input coming in. So the model is the final thing that comes out after your training and all that. That's now you can integrate into the rest of your software. And now it covers when the new data comes in, it's able to give you some prediction of what it is. And training is it's a big part of the machine learning. And it's now we take the data, apply it, execute it using this algorithm, and then it produces the model. That's the activity. So let's see. I think both Alex and Josh mentioned about the types. There are types. Supervised is the one that you mark the data saying this is husky, this is wolf, and that takes work for human to do that. And then eventually you feed all of this to the algorithm, and it's able to then, based on it gets it right or wrong, you adjust the what is that? The back propagation you call, huh? Yeah, and that adjusts the weights in let's say whatever the network that it's using. Unsupervised is now that it's able to there's no labeling of this, but you have ability to detect the algorithms is just simply looking at the data, follows whatever it is, and it's able to say, oh, look, I found some clustering here. There is this reinforced, and reinforced in the end, it's I guess there is some logic here. It's not easy to read. I guess it's small for me, but yeah, if thinking of patterns in, what is it? It's like, oh my goodness, I can't read. Massive examples of tails. Yes, then you have Is that supervised learning?
No, it's machine learning.
Machine learning, right. Okay. Then where is the reinforced learning?
Right there.
Yeah, okay. Is that using deep neural networks?
It might not. It's just different type of algorithm.
It's another what?
It's completely orthogonal to supervised and supervised.
Okay, it's not it's something. Right. You can apply reinforced learning to unsupervised or supervised. It's a method.
It's a technique, right?
Technique.
So, like, we talk about supervised learning. You usually have something called a loss function, right?
Loss function.
Like the example, the prediction that comes out of your lost, right? And that outputs some value, right? And like importantly, like the loss function is differentiable.
Right.
And so backpropagation is calculating the derivative at every single weight, and then by doing that, you see how much each weight is contributed to error.
Right.
So you can kind of scale those like in the opposite direction.
And adjust the weights based on the feedback coming in. This is right or wrong, and then so that is the reinforced.
Well, that's supervised learning. So what reinforcement learning is, instead of having like a loss function, you have a reward function. So you basically say, I want you to behave in some certain way.
Yeah.
And
Okay.
I want you to basically maximize this value. And so
Yeah.
you're kind of training the model to like behave a certain way and saying like, as you get closer to this, like I don't know how to exactly describe this, but I can kind of give you points. Right?
Yeah. Oh, okay. Maybe something like if it was a game.
Yeah.
If you fall into the ice, this is bad.
Yeah.
If you get in 2 steps to the whatever it is that you're trying to get to this ball there, then it's you put some rules into it, and now the algorithm is trying to meet those in total between the bad things and the good things, and then come to something more maximum number of that.
You see a ton of it in video games.
Video games. I think that's reinforced learning is more video games, and maybe I'm not sure if it is applied in the automotive.
Planning and control.
Huh?
Planning and controls might be applied. So it's usually used by for kind of step by step, move by move.
Yeah.
Essentially things. So you have discrete essentially like decisions that you need to do. So it can apply to multiple things.
Okay. Yeah. So obviously it can be used. So there is kinds, and there's also the approach that you can label some of the data, and then you teach you feed this is the correct, this is husky, this is wolf, and then you can then have another algorithm label the rest of it, maybe the rest of your data. There is also that.
Yeah. So I mean, so like a lot of times we have supervised learning, we'll have like a model and it'll learn how to reason about it, right? So we can pull that classification layer off, and what we'll end up with is like a high dimensional vector that describes our data. So what you can end up doing is passing a bunch of data through, and once you have that high dimensional vector, you can start clustering it, right? And then that's when you start getting to like unsupervised space where you're trying to use a model to kind of cluster stuff, and you go in and kind of draw circles around your clusters. So like, well, this is a husky, this is
then yeah.
Seeing like clearly the model is confused and it thinks both those are the same thing.
Right. So there is each of the if we talk about the algorithm, which is the core, it comes with parameters. There is parameters, part of this algorithm, which are adjusted. There is parameters and there's hyperparameters. Hyperparameters could be the number of layers in that neural network, right?
Yeah.
And there is maybe they are more they are adjusted as an initial step.
They're like the knobs you turn.
Knobs you turn.
And then parameters are like the actual weights that make up your model, right? So
Right.
stuff that's been trained by the updating. What do you think of it?
Right.
Hyperparameters like a knob we turn to try and match.
Mm-hmm.
Generally speaking, there are like two different algorithms, right? And they're kind of related, or like very related case of neural networks. So one is like prediction and inference. So this is like when things like running on the car, right? When you need to say this is, sausage, not sausage.
Okay.
And different algorithms, how you teach this algorithm to do the job it needs to do. Right? So the training algorithm related to prediction, but it's a different algorithm. So how you teach is
Right.
also algorithm. The hyperparameter
Is part of that algorithm.
usually is part of the algorithm that teaches.
Right. Because also there is a algorithm that actually does the training, right?
Yeah, so this is the algorithm that does the training.
That's what's the parameters. The knobs there are the hyperparameters.
Right.
Parameters are the ones that are tweaked as you learn, result of the learning that they change. So this neural networks and such, and you could potentially put whatever the function in each node or that weight being applied to the inputs coming in. And so those values, they change. And that's the parameters. Okay, there is features of the feature. You use feature, for example, in the terminology for representing, for example, here the distribution of the colors in a picture.
Yeah, it's how you describe the world to the model. So it's like trying to distill useful information from your inputs and like feed out to your model.
Right. It's the color of it. It's the shape.
Speed, maybe like your driving speed.
Right. All these become features. That's the terms you're using. And then we have the labels that we talked about is the one that we say, this is what we give as the input as part of, together with the data, say this is husky, this is wolf. That's or the kind of the traffic sign. Okay. So my understanding is no matter what, we got software we got to produce. We got to represent the problem. What is the problem the software needs to solve? So that expression of the problem is a step that we need to cover, so represent and describe. So I put down here some steps as we work on machine learning, and I thought, okay, the first one, we got to describe the problem. And this is the same, really similar to traditional software. We all got to know what problem the software needs to solve. A description of that is first step, understanding. So you basically write requirements. And that's basically from the Automotive SPICE, the SUI1 software requirements process is about representing what the requirements are. From machine learning, we also need to know what is the problem this machine learning needs to solve. And so I put some examples about, this is about drowsiness levels and how accurate the precision levels, what makes it valid, frame you're using, all these maybe, and also the size. You could have non-functional requirements of it, that it needs to be within this much, it needs to fit within a data or the code you're using, it needs to result in this size. So this is all representing this first step. We got to all break down exactly what is the problem we're solving. That's how I see it. Does that make sense as the first thing we do? Okay, then now we understand the problem. We need to be able to come up with data that we will use for the training of the model. And this data needs to be representing the real world examples of the achievement. Let's say if drowsiness, we need to get pictures of the images of the sleepy guy and the, if you are detecting the eye, maybe how wide the eyes are open or closed, or, the various, you need to have sufficient scenarios. You got to come up with some strategy on what is this data, what are the sources I'm going to get it from, how many of what kind scenarios we need to collect, and collecting all this data and identifying if you need to, you got to take each of the data, do some initial pre-processing, kind of like cleansing of this, preparing, and then grouping them in some data sets. Because we're going to talk in the later steps, we have to use the data to train. There is also the data used, here is called like verification, which check to see if the trained algorithm is now correctly achieving the what we said, the correct predicting the data based on the new data in this verification. Then there is this validation data. Maybe it's the one that's like your golden set that says it's a final single set that, based on this golden set of data, it's achieving the results what we said we will need to achieve in our requirements, for example. So all this data, it's one of the major activities as part of machine learning. 90% data. It's big work. Yeah. Does this make sense, Josh? Regarding data, you want to?
Yeah, I think so. Typically, people call it lots of different things. So you'll hear like training, development, and test. Training, validation, and test are the ones that are.
Yeah, you group them into sets for purposes. There's one purpose, you got to use it for training. Yeah. And there's other purposes, like to check to see if the trained data is achieving the results you want, etc.
As I mentioned before, like these are correlation machines, right? As you train these models, it's very easy to like overfit on a data distribution where like if your model is large enough, it can just learn, it can memorize your data set. Yeah. It can actually learn the function you want. It just learns the latest in your data set. And so we have this validation data set we hold out that we look at during training to say, like, are we actually learning the thing we want, right? This is very obsessive, like,
right.
How is training compared to validation?
Right.
And as you're using that through training, like, it kind of becomes like a dirty data set because you've used it usually for model function. So, like, we try to be very objective so that you have, like, that final data set that you hold out. It is kind of like your gut check before you release into production.
Right.
Which is like we require a minimal accuracy, recall precision.
Right.
Want to see before we release the model.
And that separation of these is critical because of, like you said, the memory. And so managing the quality of the data, the preparation, all of that is critical. It's a large portion of the work. It's done, and it directly impacts the results. After all that work, it didn't learn. It just memorized. It's really problematic. If the data has poor quality, problem.
Yeah. You spend a lot of time looking at data. Understanding that now. So,
right.
So I will make just like one comment. So in terms of somewhat different from kind of the V model, so like waterfall model. So what defines that your training set is good, like the quality, is very dependent on your training algorithm. Okay, so what is good training set? Like for one, training algorithm is not necessarily means that it will be good like for different training algorithm. like a good example is like how people learn, right? We don't need like millions of images, right? It also like depends what you know about the physical world, generally speaking. It's called like priors, right? No. This is how people learn. What you know about the world, how things like interact.
Yeah, once you learn one thing, you can learn the next thing a little easier. You're saying.
So, for
right?
example, to teach like a kid how a penguin looks like or like giraffe, you don't show 1,000 images, right?
No, you're right.
So you show like 2 or 3, right? And your test set is probably also can be like 2 or 3 images, right?
Right.
So it's very important to understand. So yeah, so supervising the techniques are very relevant right now, and this is how people think about it. But this is not the only way to do it.
Mm-hmm.
I think like how do we scope the data and the data collection? How do you scope the data collection or amount of data collection? What your
Yeah, I'm saying that like the definition what is like good training set is dependent not just like purely like we can define what is good, like what is the good image and like what is the good side. It also depends a lot on your training algorithm, right?
Mm.
Yeah, I mean that's you got your finger basically on the fact that neural networks don't think like humans, right? It's all pattern recognition and it's memorized patterns. And it's like humans can learn from 3 examples, right? Things where like you can kind of inherently say like, well, neural networks are actually extremely brittle.
Yeah, this is fine, but like I think we're talking about machine learning and just like neural networks, and also neural networks you can also teach like differently.
Mm.
So
the trick is if we can then train them on various things, and somehow if we can make them that it's easier to learn the next new thing.
Exactly.
That's so that it's not like we have to give these thousands or whatever.
Yeah, generally speaking, there's like a famous theorem specifically for neural networks.
Yeah.
Which says that generally speaking, it's enough to have like 2 layers, more or less, to teach anything. To teach it. So those
2 layers only, teach anything.
Yeah, anything. Those layers can be like ginormous.
Oh, really big layers.
So it's a theoretical thing, right? Mm. So you can have like a very simple network. It is like in terms of architecture that you'll do whatever you do, and Michelangelo together with Raphael. But what this theorem doesn't give you a way how to teach this neural network.
Yeah.
Okay, so yeah, theoretically this network exists. How to get there, you don't know. So and you don't know this is exactly the training algorithm, right? So depending on your training algorithm approach.
Yeah. So the training algorithm is critical to make this effective and efficient. Otherwise, you cannot just simply take any neural network and, all right, like I'm just going to teach something. And sure, there needs to be some more, that's the definition of how you're going to train is the key. Yeah, for sure. And that's that continuous learning from you start with one way. Oh, okay, it became that the algorithm just memorized. Okay, now I'm gonna train like this. That training strategy, which we're gonna come to that as a later steps, that's critical. I see 2 new colleagues. Are you VJ?
right?
VJ loves me. Welcome. And are you Rami? You're John. Okay, no. Okay, welcome, guys. So we're kind of moving into the. So what we can do, Sujin, is you can put your name tag on this blank one. There is actually a. I'm sorry. Okay. Yeah. You're not. So, right. Here, yeah. Yeah, Mark. Okay, so now, so far we described what is our problem we're gonna solve. We talked about the data. We talked about using data for different purposes. And following step, I understand, obviously all these are, there is iteration across these. It's just I'm capturing in my mind the steps at the big picture. We need to figure out the algorithm we're gonna use to solve the problem using that data we came up with to train. And so there is this approach to figure out, okay, which algorithm we should use. There is a selection to be made, and then also configuring of this algorithm needs to be made. So there is, I mean, okay, in traditional software, we reuse software, right? We can consider, we can take something or use this function or that logic or algorithm. There is some decisions we can make, configuring. We can take some existing library or such. There is some decisions, but this purpose is different because this algorithm is not just exactly what's in the code. This is something is used to learn from the data to come up with the final model. So the purpose is different, I feel. And here we figure out what are the options, come up with some criteria. How are we going to choose which algorithm to use? So there is the considerations of trustworthiness, which is, I think, a big word. How do you come up with the trustworthiness of this algorithm? And then there is the explainability. Can you explain it to someone, or are you able to understand? Could be some criteria. You usually select multiple algorithms, and I think then you train them and check to see which one ended up with the better result. And is that how it works, Josh?
Yeah, basically. I mean, explainability is the really important depending on what business you're into. So like when I was doing surveillance in banks, everything has to be explained. So that really limited the ability to use external values. Trustworthiness really does come down to data set design, whether or not you've covered all the cases you want to describe and understand. That's kind of why that, like, you spend 90% of your time making sure that your data set is representative of the problems that you want to solve.
Right.
But yeah, you typically, you can try a whole bunch of different algorithms. There are some lighter weight algorithms that are sometimes a better option, right? But, I particularly enjoyed that, like, AI is a marketing term.
Okay.
There's this great joke that's like, it's ML when you're hiring, AI when you're fundraising. It's just a regression when you're in production, which is pretty much the simplest model you can possibly build.
Is the best, right?
And it's where you should always start.
So there is already, in the market, you can get these. Some of them are like free, I think. You could get algorithms. You can make algorithms.
Yeah, I mean, most of this stuff is pretty much like the algorithms are described in frameworks for the most part. Right?
And that's part of the training framework too, right?
Yeah, so you're leveraging some tools that you have like Python or MATLAB where you have like toolboxes that you basically bring in, right? And they'll have all those classifiers described for you. And you bring your data to that algorithm, right? And so
right. So you can configure all of these hyperparameters that we talked about through MATLAB, for example.
I'm still learning.
You're learning. Okay.
I have heard that I have a couple of toolboxes. Yeah.
Josh said he used it.
Yeah, I put that a little bit. I'm a little bit more Python. Getting better at MATLAB since I've done ASPICE concepts.
Okay. Okay. Python is very common to come up with configure those frameworks.
Yeah. So you've got like TensorFlow and PyTorch, which are popular for neural networks, but then there are other kind of frameworks like scikit-learn, which encapsulate a lot more of the other sort of classifiers you can choose to use.
Mm.
And then your kind of selection process is somewhat decided by like the type of data you have and how it kind of.
Don't you come up with some criteria first to see how you're going to select?
Yeah, okay, so there's also metric selection, right, which is an important part of model development, which is to say, like, can we mathematically describe the kind of behavior we want?
Okay.
And so you typically, like, you kind of like, you have a loss function which can be useful, but then you usually will like try to have a few metrics basically to describe that, and then you can look at the distribution of the metrics basically over your data set to get an idea of like how consistent your model is. So like build your data set, build your metrics, then choose your algorithms, train them, and then use the metrics to evaluate the various different models you have, and then based on the performance of the data set, you kind of try to choose your best one that you cross the most too.
Right.
Like we talk about accuracy, but we also talk about like precision and recall, which are measuring things like
right.
And so typically you have to kind of tune your classifier like towards whatever application you are, and you're usually kind of balancing out like whether you want the model to be very confident and predict a lot, or you only want it to predict when it's like very, very confident.
Some algorithms could be more if you want the accuracy, or you said confident the results, how confident you will be at the results.
Yeah.
Okay.
You look at things like confidence.
That's trustworthiness, isn't it? In the end, that's the trustworthiness. So when the algorithm says this is ASCII, how much trust do you have in this? That it is really ASCII. Okay, I mean.
Yeah, well, and I guess in the fact that a lot of classifiers, you're not really getting a probability out. And a lot of classifiers are overly confident. There's sort of an area of research to try and train models that act like they predict their confidence more.
Okay.
It's always funny at companies, and I'm like, we're doing a confidence metric. And I'm like, that's harder than the model.
So, I mean, obviously they're marketing, then they're saying, hey.
Yeah, so instead of like saying, hey, model, like, how confident are you? You usually want to have a very large representative data set, right? So we're talking about data set design.
Right, there's total relationship to that as well. And as Alex said, you may not start from a raw, totally untrained, pure statistical logic matrix, whatever algorithm. You may start with some model that's already some.
Yeah.
It's able to detect cats or the dogs, and now we want to do about the different kinds of dogs or something,
Yeah,
you could.
And what that's called is transfer learning, and whenever you can do it, you should.
Right.
Yeah, because it just saves you the amount of data you actually need to bring to the table, right?
Right. It reduces because it already has certain ability to detect the dogs. Now that's useful when you are detecting the comparison between the other kinds of. Okay.
Yeah, because there's kind of layers and they build on each other, right?
Right.
So like the early layers are doing things like kinds of energy. So it's like for pretty much all vision things, you kind of learn the same filter. So a lot of the time you like reuse the first couple layers from the model. And then when we do learning, like.
Oh yeah, you could do that too, right? To say, hey, this takes care of to detecting the cat or the dog. Now we know the dog, but we want to know something more about the dog. You add and you train the next layer down, and that now does the next thing.
There was a really interesting story maybe 10 years ago about facial recognition. Right? And like from the Western side, like the US, they were approaching a very pure AI, right? Mm-hmm. There was privacy issues and stuff like that, so they had to. But in China, they just started taking pictures of everybody. They just collected a ginormous data of people's faces. Yeah. And I feel like now everybody can do facial recognition, but it's that algorithm that you talk about has changed, right? Mm. From being just brute force data set to just this super finesse AI, and now it's somewhere in the middle. And I feel like it's.
So what you're describing there is something called single shot or few shot learning, which is it's kind of infeasible to teach a model to like learn like everyone's face, right? So what you end up training is like a model on some set of faces, which learns to extract features that describe the face, right? And then as you want to add more people into it, you can use a couple examples to say like this is the vector that describes this face. And so then you can start cutting up like your entire application space. So like this small part of my entire like space that all feature vectors describe it is like this person.
Right. But I think we've come to that.
Yeah.
I think originally they said, how does, I look at somebody for 5 minutes and I'll remember them.
Yeah.
Right?
Yeah.
And try to model your thought
How do you do
process.
that?
It was just way too complicated and they just couldn't get that to work.
Yeah.
Right? They
Well,
couldn't teach a machine to think like a human, but that was just not going to happen.
Yeah.
But
Not yet.
So they're sort of kind of arrived at somewhere in the middle where it's a data set and some sort of learning, right?
So it's kind of like a two-phase thing where you train it on like a classification task, for instance, but then we call it like the classification head. So like the last layer, usually like take like your high dimensional vector and like reduce it to like your encoding of like this many people. And so you kind of do your classical training, but then you get very clever in how you kind of leverage the model to make it more extendable. Because like obviously it's not desirable every time you want to add a new person into your data set to completely retrain the model. So
No, that's crazy, right?
very
Yeah.
Clever about leveraging that model, only training it so many times.
Yeah.
Right.
And being able to update it quickly. But yeah. It's very clever. I remember when that stuff started coming out.
Yes.
Because there was a theoretical limit to how many faces you could actually learn in the model. And I remember there was like hardcore conversations about that as we started coming to light.
Yeah.
So yeah, this brings us to one of the major steps is training now. We got data, we picked the algorithm, and I think it sounds like the algorithm, it's not just it comes with the whole framework that has all those hyperparameters and such. Everything is ready. We now train. And basically, the strategy, the approach is so important. I think coming up with, do you guys figure out, discuss, write down some, what should be the approaches, training, what is our strategy to avoid those overfittings and such, the different strategies you're going to apply. So I think that's should be written down somewhere. And then you execute, and it adjusts the parameters of the algorithm. You trained maybe 2-3 of these, and based on whatever your criteria may have been, you say, oh yeah, I go with this one.
Yeah, I mean, again, it's your metric selection and data set creation is a large part of what drives this, right? And the best practices, which you showed with the partitions of the data set, right? And through the kind of trifecta of those things, you begin to understand your model, and then you basically improve on that forever.
Yeah.
So you just kind of continue to always improve.
Well, at some point you gotta stop the training, right? You can't go forever. Time runs out too, right? And there needs to be some criteria. When am I gonna stop this thing? When am I gonna say this is done? For good or bad? You could say, no, okay, let's stop. This is not going anywhere. It's not gonna work. Then maybe you have to then start over somewhere.
Yeah. So when you select those metrics, you try to understand, like, what are they telling you about behavior in the model? There you try to say, like, well, we want to see it at this level before we're confident we want to roll it out.
Right. It may even reach a point that the accuracy, let's pretend, is one of the metrics you're looking at. It's not going to improve much. It's like, oh, I'm like 0.0 something. Like, okay, I mean, is this worth keep training? You may say it's not. That maybe you need to figure out, come to decisions. All of that, I say, is the strategy, and then execution of it. Then finally looking at it to see out of the 3, whatever we trained, what did it become is the one that we want to move forward with. There is some terms here, again, that is used in the machine learning. There is the bias. I think it seems like to be the, if this is something you want to avoid.
Yeah.
And yeah,
Absolutely.
right. And there is a data set could be biased because you all got the certain, most of it is the certain kind, maybe category, because it's not distributed well. It's not representing our world reality.
Yeah.
Distribution is twisted, could result in this. And then evaluation is then the checking to see that if the metrics are achieved, are we making the good predictions and how well is it? And trustworthiness, it's a complex topic, difficult to achieve, I understand, and that it needs to be. Is this going back to even as well the consideration of can we trust this thing? How confident we are, and safety will need to be part of that. Yeah. After the last step is the evaluation, I think now, and this is all iterative, right? And evaluation, there is that validation step. You do that once, I understand, as that golden set, let's say, called, and executing the data. That data, it's only done once, but there is this set of this verification is repeated, maybe train, verify multiple times, and eventually you just do the validation and done.
Yeah. Exactly. You absolutely have to have a set of data that you have held out that you don't ever look at or make decisions based on. But that's like why that golden set you're referring to is so important.
So during verification or this evaluation, it's not learning anymore. You stopped learning, right? Because then you don't want to adjust the parameters for this. You stop, the algorithm is not learning at that time. It's just like predicting based on data without adjusting any of the parameters. And then once that final golden validation is done, and assuming it fit the achieved metrics, then you release it. Now it's something you can integrate into the rest of the software. And so capturing a strategy of how you're going to go about doing this is important. Of course, the data sets, the specifying of the scenarios you're going to use. It's kind of, those scenarios could be our use case scenarios on coming up with any kind of test cases that we come up with. But in this case, you use it to select the data based on these scenarios. Is it going to be the rainy day or the cloudy day or I'm not sure, looking from the side angle of whatever the scenarios you want to cover, it will be. So this is what I
go back for a second.
Please.
I have a question about this.
Please.
So for validation, there is only one dedicated data set, which is only used once in one validation cycle.
That's what I understand.
What if you fail validation? What happens?
Then you're done.
You're done with.
Game is over.
And do you use a different data set to
revalidate?
You may not just look at one number, right? If you have a descriptor of your data set, you might break it down. Right?
Yeah.
But the main thing is, like, if you fail on your validation side, you don't want to make decisions based on it. You want to go back. Okay. Also, I can't agree on just keep calling this validation set because this is the test set we're talking about now. Because most people you'll call it train, validation, and test, or train and development, and then test is like your final hold out test set. And the only reason I'm saying this is I don't want you guys to go out and confuse your machine learning engineers. But the really important thing is that a final holdout data set don't make decisions based on it.
Yeah.
It's just a go, no, go. And then if it fails there, you have to go back to your training and validation data set to reiterate and try to push them back.
You have to change something. You go back. Either your data change, your hyperparameter change, I mean, I guess you can even take a different algorithm.
Yeah.
You know, you whatever you have to change to now starting over from there.
Okay, just come back to the question. So then, with the test data set, is the same one you'd use for the next iteration?
Okay, yeah, you do start, yeah, yes.
I mean, that's your test. That's what you define as success, pass or fail.
Yeah,
So you always use that.
yeah, you typically try to make, so like when you're going through the training loop, the holdout data set that you have for that, you try to make all of your decisions based on that and all of your tuning based on that. And then that's just really just that go, no go to be released in production or not. And you try to limit it to just that. So you try your hardest to not allow it to influence and make.
Yeah.
Yes. So, but yeah, you have recycling the data set. I mean, that's largely like the cost standpoint.
Right.
The biggest cost in all the acquisition, like making sure you're representing all the points.
Right.
If we could also change some of the
Yeah.
Yeah. And that model selection stuff is probably part of like the training cycle. Like,
It's, yeah. If the evaluation fails, yeah, you may change the model
Yeah.
that your algorithm or hyperparameters, whatever it is, your training approach as well.
So a lot of the time you like look at numbers and then back and you're looking at specific examples and trying to reason failing over.
Yeah.
So Tesla kind of like changed the game in automotive, right? So you have like OTA right now. So like over the air updates. So it used to be like how cars were built, especially it's like a project-based approach, right? So you come together, put all the widgets, put software, ship them, do it like 5 years in a row, same product.
Yeah.
So like no longer, right? This is, at least like Tesla doesn't do it, and there's like huge push of huge pressure on OEMs like to change their ways. So anyway, so everybody like more or less everybody talking about the TA. It means you change your software, including your models, when your car already in the wild, right? And it's like it's interesting question, like what do you do, right? Because traditional validation process like VMV is very expensive. And like if you also like add on top of this like homologation, so do you go and start, like running same homologation in every country?
Right.
But generally speaking, it's like it's heading in this direction. And part of it, yes, your validation of test set, it will grow all the time. Because like your ED grows, right? You want to support different scenarios. So like in terms of like this sort of terminology. So, it's not static like anymore.
No, yeah, data. So you may come up with, from all the learnings, if you already got something out in production, whatever you learn, you could then come up with a different validation set or evaluation data set based on all of this. And because certain corner cases somehow wasn't there, maybe it's growing, it's becoming more complete and concise, maybe, and then eventually you improve upon whatever was learned. You got a new model coming out, and you test it against this new evaluation data set, and it gets through the released to the customer through the over-the-air updates.
Exactly.
Yeah.
So it's sort of like short terminology, right? So you're trying to reduce this sector of unknown unknowns, right?
Yeah, unknowns, right? Right. Right. And that's also the operating design domain topics come in as in the automated driving, that it's like, okay, it's in this domain, it's okay. it's only it works. Otherwise, it won't work. Let's say the automation. Thank you, guys.